Hi, this is Mrs. Villette, and this video is to finish off the 5.1 antiderivative notes. In this video, I'm going to go over the notes that are already filled out, so I'm just going to kind of narrate and point out important pieces in the notes. The idea being that you can pause and write down what you need to write down, or you can copy down the notes first and then come back and just watch the quick explanation. So hopefully after this will go a little bit faster. This is just a reminder of what we talked about before, the reverse power rule. So if you want to find the antiderivative of a power function, you simply add 1 to the exponent, divide by the new exponent, and then add a constant. And an example of that was the antiderivative of x to the 4th would be x to the 5th over 5 plus c. We talked about using the integral symbol, and in one of the classes we actually finished this example 3, in the other class we didn't. So just to go over it briefly again, we're not looking for some sort of reverse quotient rule here. What we're trying to use is the only rule that we really have right now, the reverse power rule or antiderivatives of basic functions. So the first thing I did was distribute the division and change the root to rational exponent form. Then I simplified my exponents, and now I'm in a form of 2 power functions, and I can take their antiderivative. So the symbol I use is the integral symbol. So the integral of this new simplified function with respect to x. I'm going to add 1 to the exponent, so 3 halves plus 1. 1 is 2 halves, is 5 halves, divided by 5 halves. Negative a half plus 1 gives me 1 half divided by a half. Then I invert and multiply, and of course I have my constant here. The last step that we need to do is actually find the value of the constant, and that's where we use the information that they gave us, f of 4 equals 1. So I'm setting the function value equal to 1 and plugging 4 in for the x value. Remember that a 1/2 power is a square root, so here I'm taking the square root of 4 first, then raising it to the 5th, which is where the 32 comes from. And then we solve when we get c equals negative 99/5. I do want to pause here and just give you a picture of what this looks like in Desmos. So what I have in Desmos is I have the original function here, and I've got the antiderivative set up with this integration constant c, and I've got this c set up as a slider. And unfortunately, I can't really video myself moving the slider in Desmos, but you could try setting this up yourself. So if we think about this like a regular function and its derivative relationship, then we're thinking about this green function as my function, and then we're thinking about the red function as the derivative of that. So f prime of x equals f of x. And we can see things that we would expect, like my original function. Remember, the green is actually the function. It's always increasing, so my derivative, which is the red function, is always positive. We can see that it looks like there's an inflection point in the original function right about here, and that corresponds with the minimum on the f of x, or the capital F prime of x. But the point I wanted to get at here is if you move the value of the slider, what you're basically doing is you're moving this function, the capital F, up or down, and we can see that eventually if we move it down far enough, we are going to pass through this point 4, 1. And that's what that particular value of c did for us. Okay, so the next part of the notes are just the sort of basic antiderivative formulas that we can work with. We're going to base them all on our knowledge of derivatives. So we know since the derivative of sine is cosine, that means the antiderivative of cosine is sine of x plus c. Remember, we're always adding that integration constant. Derivative of cosine is negative sine. We're actually going to flip this one a little bit and say the antiderivative of sine is negative cosine. So we're not putting the negative with the sine, we're putting it with the antiderivative, knowing that when I take the derivative of cosine, I'll have a negative times a negative, which is going to give me that positive. Derivative of tangent is secant squared, so antiderivative of secant squared is tangent of x plus c. Derivative of secant is secant tangent, so the antiderivative of secant tangent is secant x plus c. So let's go through an example that we haven't been explicitly taught to do, but I think we can figure out. We're doing the antiderivative of cosine of 3x. So remember, we're trying to find a function capital F of x, where if I take its derivative, I get cosine 3x. So I know my original function needs to be some sort of sine function. So we start with maybe sine of 3x, and you realize that when you do the derivative of sine of 3x, there's going to be a 3 that pops out in front from the chain rule. So you just divide by 3 to account for that times 3. So if we're checking, when we check, my f prime of x would be the derivative, be 1/3. Derivative of sine of 3x is cosine of 3x multiplied by the derivative of the inside, which is 3, and the derivative of the constant is 0. I can see the 3's cancel, giving me my original integrand. That's the function that's inside this integral symbol. Okay, this last table just sort of summarizes all our antiderivative rules. It adds a few new ones that we haven't talked about yet. Most notably, we've rewritten the reverse power rule. So add 1 to the exponent, divide by the new exponent. Now that only works if your n is not equal to -1. And the reason it doesn't work when your n is equal to -1, that would be the function 1 over x, and its antiderivative is the natural log of the absolute value of x. I'll talk about why it's absolute value in the next example. E to the x should be pretty straightforward. A to the x, remember that the derivative of a to the x is natural log of a times a to the x. So when I anti-differentiate, I have to divide by the natural log of a to counteract that multiplication. Cosine, sine, secant, tangent, we just talked about. And then these, of course, are functions where this integrand is the derivative of the inverse tan. So its antiderivative is inverse tangent. And this, 1 over the square root of 1 subtract x squared, is the derivative of arc sine, or inverse sine of x. So I said I would talk about why the absolute value is there on the 1 over x antiderivative. And the reason is the 1 over x function, its domain, so the 1 over x is this blue, is everything but 0. But natural log, which is this dotted red line, is only everything to the right of 0. So if I want a function and I want to find its antiderivative, I need to be able to have them be defined on pretty much the same domain, maybe differing by endpoints. So one could include 0 and the other one wouldn't, but I don't want them to be so drastically different where one of them includes negative numbers and the other doesn't. So the way that we fix that is we do the antiderivative of 1 over x as the natural log of the absolute value of x. Putting that absolute value in there just means that we're now allowing x to be both positive or negative, but still not 0. So completing the other half, if you put these two pieces together, these red dotted, that is the natural log of the absolute value of x. Now when we take derivatives, I know I mentioned this in the notes at least once, you really should be saying 1 over x for x greater than 0. We get kind of lazy and we don't do that. So really we want to be thinking about the function and its derivative, or the function and its antiderivative, having very, very similar domains, not a whole entire chunk of a domain missing. Okay, our last example, which may be something that we end up doing in class the next day, is this motion example. So we know the derivative relationships between position, velocity, and acceleration. So now we're going to look at these from an antiderivative perspective. Now this is something when you took physics that you probably would have just been given formulas for. But we're going to start off with an example where we know the acceleration due to gravity, 3.75 meters per second squared on Mars. And we're going to throw a rock up from ground level with an initial velocity of 5 meters per second. How long does it take the rock to hit the ground? Well, we need to find the position function. So we're going to start by saying s double prime of t is my acceleration, negative 3.75 meters per second squared. The negative is because gravity is pulling down. If I want to find my velocity, my s prime of t, I need to do the antiderivative of acceleration. We have to get a little bit tricky here, and we have to say my acceleration is negative 3.75, and I'm going to call that t to the 0. So I'm anti-differentiating basically a t to the 0. Using my reverse power rule, I add 1 to the exponent, divide by the new exponent, and I add my integration constant. My integration constant here is just going to be the initial velocity, because I know if I plug t equals 0 in here, this will just 0 out, and then I will have 5 as what I want my integration constant to be. Now we go one more level up, so we need to do the antiderivative of my velocity. So position is antiderivative of velocity. Now this is my velocity. I'm going to do the reverse power rule, add 1 to the exponent, divide by the new exponent. Here, same thing, make it t to the first, it was t to the 0, plus initial position. Now the problem stated that the rock was thrown from ground level, so my initial position is 0. That gives me my position function. I want to know when the rock hits the ground, so I want to know when my position, or my height, is 0. So s of t equals 0 means 0 equals this function, which I can factor a t out of. That gives me t equals 0, which is just when the rock was initially thrown up, and then t equals 5 over 1.875, or about 2, not about, exactly 2 1/3. So the rock hits the ground after 2 1/3 seconds.